All right, everyone, we are headed into our next session. With that in mind, I want to introduce Aaron Andalman, who is the Chief Science Officer at Cognitiv. He's going to be telling us a little bit about deep learning for customer acquisition. Welcome, Aaron.
Thank you for the introduction. It's great to be with you today, at least virtually. Thank you so much for attending the Digital Insurance Summit 2020 during these unusual times. I really appreciate everyone taking the time to listen in. So my name is Aaron Andalman. I'm a co-founder and the Chief Science Officer at Cognitiv, where I apply my expertise in neural networks and computer science to challenging problems in advertising. Today, I'm going to tell you about the use of deep learning for optimizing incrementality and driving customer acquisition. So these days, marketing messages can be communicated in ever more precise ways. The technology is pretty amazing. We can direct specific messages to specific users at specific times, and we can condition that on specific weather conditions or specific devices, et cetera, et cetera. And this remarkable technology puts what has long been thought of as sort of a holy grail of advertising, the idea of the right message to the right person at the right place at the right time within technological reach. But ad tech, as it currently stands, isn't quite ready to deliver on that promise. And this is in part because different vendors within the ad tech space tend to focus on optimizing different aspects of one's marketing strategy. So for example, one vendor might optimize the audience while another vendor optimizes in what context you show your ad or your creative, etc. And this siloed ad tech organization, it leads to disjoint and therefore suboptimal and sometimes partially manual solutions. And so at Cognitiv, we're focused on pushing ad tech into its next phase, a phase we call algorithmic advertising, in which multiple aspects of these marketing questions are optimized together or jointly. However, before one can start optimizing anything, one has to decide what you're trying to optimize. You have to define your objective. So given that, let's start with how one assesses their advertising performance. In a world in which many of us are running multiple advertising campaigns through multiple different channels and vendors at the same time, assessing whether a particular vendor or channel is performing can be difficult. And in the performance advertising channel, which is the space Cognitiv works in, a very common key performance indicator, or KPI, is cost per acquisition. So cost per acquisition, or CPA, sounds like the perfect KPI. Of course, you want to optimize the cost of acquiring a new customer. You'd rather acquire a customer for $25 than for $50. The problem is that the name cost per acquisition is actually somewhat misleading. It doesn't typically, or it doesn't always accurately reflect the cost of acquiring new customers. So why is that? Let's just define CPA to begin with. So CPA, or cost per acquisition, is typically defined as the cost of the media divided by the number of conversions attributed to that media or to the campaign. And the concern here is with the denominator. So the issue is that when computing CPA, little or no attempt is made at determining how many of the conversions in the denominator would have occurred if you hadn't run the ad campaign at all. And this is a problem because it means the KPI can be gamed, meaning it can be minimized in ways that are not aligned with your goals. For example, someone could build a model that predicts who will buy your product even if they don't see an ad. And then they could try to show those people ads just to get the attribution, even though those ads aren't influencing those people. So in general, it's always bad to have a KPI that can be gamed. Fortunately, there's a solution to this issue or this concern. And the term the field is using to refer to this solution is incrementality. So incremental CPA is a different KPI that addresses the primary shortcoming of CPA. So specifically, the denominator is adjusted so that the conversions that would have occurred organically, that is, the conversions that would have occurred even if you hadn't run the ad, are not counted. And this means that it accurately reflects the causal influence of your creatives on their audience. And it means that it is not subject to manipulation. But this begs a question: how can one accurately measure the number of conversions that would have happened if you didn't show ads? So measuring incremental CPA requires a careful scientific approach, but it is possible. And the approach is perfectly analogous to the methods pharmaceutical companies and the Food and Drug Administration use when trying to determine if new medications are effective. Essentially, one has to run a randomized clinical trial. And in a randomized clinical trial, a random set of participants receive the medication, and a different group, typically called the control group, receives pills that contain none of the active ingredient. And to measure incremental CPA, you need an analogous design. But in this case, the experimental group sees your creative, while the control group sees an ad unrelated to your campaign, like a public service announcement. And then one can measure if there's a difference in the conversion rates between these two groups. And if there is a difference, then we can attribute that difference to the fact that you ran your ads. So while this may sound relatively simple, there are actually a lot of important potential pitfalls. Just like running a clinical trial is challenging and requires a well-designed experiment, measuring incremental CPA is similar. So there are a couple of high-level critical things that need to be true in order for a measurement of incremental CPA to be accurate. So first, users must be assigned to the two groups completely randomly. And this is important because if the two groups don't have the same organic conversion rate, then the whole measurement is invalid. So if we're going to be measuring the organic conversion rate, we need to have the control group be similar to the same as the experimental group. And then the second critical thing that needs to be true is that both groups have to be treated identically except for the creatives they see. If there are any other differences in the treatment, then that difference might be responsible for differences in conversion rate or the differences in performance, and we wouldn't necessarily be able to attribute performance differences to the creative they saw. So the reality is that some vendors try to cut corners and report what they call incrementality without actually running a control group. For example, some vendors might try to approximate a control group using lookalike modeling, saying, hey, these users look a lot like the users you showed ads to, and their organic conversion rate was X. But this approach is not scientifically rigorous. For example, the Food and Drug Administration would never allow an approach like that to be taken when trying to test a new medication. So this slide shows a simple schematic of what incrementality looks like when done right. So first, users are assigned to a group randomly with the flip of a coin. And importantly, the proportion of users assigned to each group has to be consistent with the relative budgets associated with the experimental group and the PSA group. Okay, then the users in the two groups, as I mentioned, have to be treated identically. And this means the same algorithm has to be used when deciding which request to bid on. It means the same bid price calculation has to be applied to both groups. The same frequency capping, the same filtering rules, all of these details need to be the same. And if you do this, then in the end, any statistically significant difference between the performance of the two groups can be attributed to the advertising campaign. So bringing this back to the beginning of the talk, this measurement is accurate even if you're running if you're running campaigns in other channels or with other vendors, because the users are assigned randomly to the groups, both groups will be equally affected by other campaigns that you're running. Okay, so to summarize the first part of the talk, we talked about how CPA has flaws as a key performance indicator, but incremental CPA provides an accurate and scientifically sound measure that isn't gameable. We talked about how this measurement is accurate even in multi-channel, multi-campaign settings. And the fact that it's accurate in these complex situations makes the overhead cost of running a control group absolutely worth it. And 3 is sort of a bonus that we haven't talked about, but it turns out that showing that running a control group has some very important additional benefits, which is going to be the topic of the remainder of the talk. So it turns out that the data you acquire by running a control group, by showing, say, public service announcements, is not only useful for measuring incremental CPA, but it also provides data critical for optimizing incremental CPA. So knowing your ads are getting you, say, truly new customers that you wouldn't have gotten organically for $40 each, that's great. But it would be even better if you had the tools you needed to push that number down to, say, $30. And that is what control group data can do. So in the second part of this talk, I'm going to discuss how we optimize incremental CPA and the role that deep learning plays in this process. Okay, so what does it mean to optimize incremental CPA? Essentially, it means delivering on the promise of right message, right user, right place, right time in an algorithmic way. It's saying to minimize incremental CPA, one has to find the pockets of inventory in which your creatives are the most effective or most influential. And the key idea here is that the control group data set provides a necessary and critical baseline for identifying those pockets of inventory. So to illustrate this idea, let's consider these simple heat maps. So imagine the 2 axes of this heat map are whatever features you think are most interesting. Let's say the x-axis is age and the y-axis is income, or whatever's relevant to you or your product. And the yellower the map is, the more likely those users are to convert. So in the left group, let's say we ran an ad campaign and we looked at where users were converting and along these 2 dimensions, and we say, hey, look, there's actually 2 clusters here where we see high conversion rates in this plot. There's sort of the lower right cluster and the upper left cluster. And you might think, oh, well, these 2 groups are performing equally well. My ads are equally effective in those 2 groups. But if we run a control group, we can learn some details about this, or we can learn where the ads are truly effective. So if we look at the middle plot, we can see that the lower cluster is actually, this is we're now analyzing the data where we showed PSAs. We would find, oh, look, the lower cluster actually is converting at the same rate in the control group data, whereas the upper cluster is converting at a lower rate. So this is telling us that actually the ads are only having an influence on people in that upper left cluster. And we can see this by subtracting the 2 heat maps and showing us the incrementality, which is revealed by comparing our control group to our experimental group. Now, this simple example illustrates the key idea that you need a baseline to know where your ads are effective. But in reality, the data is not this simple. In reality, there's not just 2 features you want to consider when deciding where to show your ads. There are hundreds of features. There's time of day. There's what website you're on. There's features related to users' interests, et cetera, et cetera. So you don't just have 2 dimensions, you have many dimensions. And this high dimensional data doesn't come in the form of a clean heat map that can simply be subtracted. You can't simply compare your baseline data to your experimental data because the data is discrete samples or discrete points in like this high dimensional space. And each of these points doesn't come with a conversion rate. Your data is often labeled in a binary way. So you just have a list of converters and non-converters. And to illustrate this, I'm showing this 3D scatter plot here. Each of these points represents a user. At Cognitiv, we represent users using high dimensional embeddings. And here we're reducing that dimensionality to 3 so we can look at it. And the orange points are showing us users who converted. And you can clearly see patterns in this. And the goal would be to compare the patterns in this plot, right, in this sort of high dimensional space between the experimental and controlled data sets, and find clusters of inventory where the conversion rate was higher in the experimental set when they saw ads than the control set where they didn't see ads. The challenge is that identifying subtle patterns in high dimensional binary data is challenging. And this is where deep learning comes in. So what is deep learning, first of all? So deep learning is an advanced subset of techniques within the broader discipline of machine learning. So specifically, deep learning refers to the use of artificial neural networks with multiple hidden layers. So that's a lot to unpack, but deep learning, to sort of put it in sort of a more culturally connected frame of reference, is largely responsible for sort of the enormous amount of excitement that we see in the media and the news and industry in artificial intelligence that has occurred over the last 4 to 8 years. So deep learning is the reason computers are suddenly able to understand human speech, think Siri or Alexa. And it's the reason that Facebook can recognize your face in images. And it's also the reason why self-driving cars are suddenly on the horizon, even though cars have been around for more than 100 years. So what makes deep learning so powerful? Well, in a strange way, it actually relates to this cat here on the right side of the image. So recognizing an object like a cat has historically been a problem that humans could do with ease, but that computers struggled at. So cats come in so many different poses, so many different colors, and photos can have different lightings that historically computers just had a hard time recognizing the commonalities across all these different views. So there's these, recognizing a cat requires like understanding complex concepts and patterns, and programmers were simply unable to describe that to a computer. But deep learning has elevated computers' ability to find patterns in high dimensional data. And it's actually elevated that ability to superhuman levels. Today, deep learning is allowing computers to read X-rays at greater accuracy than doctors. It's allowing computers to play extremely complex games like the game of Go, which AI researchers didn't think computers would be able to do for another 25 to 50 years. It's allowing them to do that today. So today computers are exceeding humans at this complex game. And it's also changing the way trading happens on Wall Street. And it turns out that these pattern recognition abilities that deep learning is bringing to computers is actually relevant to marketing and advertising. So if deep learning has so much power, why isn't everyone in programmatic advertising using this technology? Well, it turns out that there's some real challenges to bringing the pattern recognition ability of deep learning to bear on programmatic advertising. So first, running deep learning or neural networks is notoriously compute intensive. And this isn't naturally compatible with the millions of bid requests that need to be analyzed every second in online advertising. So at Cognitiv, we've worked hard to overcome this hurdle over the last 2+ years, by building a deep learning platform that's capable of handling this compute. And that involves solutions like moving part of the neural network inference process offline and caching those results, and also optimizing how many inferences can be done on a CPU per second. And together, these have allowed us to overcome this challenge. And second, deep learning, a second challenge to bringing deep learning to the field of marketing is that neural networks are typically best at finding patterns in inputs that are continuous numerical features. But much of marketing data is categorical. So a user will be like on a list, like, you know, they either are into shoes or they're not into shoes, or they're in this income bracket or they're not in this income bracket. So often the data that marketers have to play with is categorical data, not sort of continuous numerical data. And so at Cognitiv, we've addressed this by developing what are called high dimensional embeddings that allow us to convert categorical data into continuous data. And so by overcoming these hurdles, we've been able to demonstrate that the pattern recognition ability of deep learning has significant value for advertisers. And so to demonstrate that, I just want to show you this, this comparison. So here I'm plotting, I'm comparing the ability of two machine learning models to predict which impressions in held out data will result in a conversion. And the first model is a logistic regression model, which is a workhorse in the field of ad tech. And this model does about 150% better than chance at predicting who will convert. And that level is consistent sort of no matter how much data we provided. It sort of ramps up until they have about 10,000 positive labels, and then it's flat. But deep learning does substantially better. So even with a small data set, it's performing more than at more than 200% better than chance. And as you add more data, as their data set grows, deep learning outperforms logistic regression by more and more. So this demonstrates the potential of the pattern recognition of deep learning for understanding your data sets. And to see this in action, let's look at a case study from our work with a Fortune 100 insurance company who's running always-on advertising in multiple channels. And this client knew that as a result of all those different channels, organic conversion rates are significant, and therefore they wanted to use machine learning to try and drive lower incremental CPAs in a specific channel. And so after collecting experimental and controlled data sets, we performed the methods I've sort of described to you today. We trained two deep learning models to predict the likelihood of conversion in it with and without seeing ads. And then we bid on inventory where the difference in that prediction between the two models was large. So we bid on inventory where the probability of converting when seeing an ad was high, but low when they didn't see the ad. And over the first month, with a relatively small amount of data, we were able to drive 28% higher conversion rates in the experimental group than the control group, showing that we could drive real incremental CPA. But the story gets better because this began as a test campaign at about relatively small budget, 50K per month for 3 months. But it has evolved into an ongoing relationship that has lasted more than 2 years. And over this time, as we've acquired more data, the deep learning models have continued to improve, such that we're now continually driving 100%, 150% incrementality with and at scale, so with much larger budgets, about 10x the budget. And this, I think, highlights perfectly the power of algorithmic advertising and deep learning to deliver on the promise of right message, right person, right place, right time. Now, deep learning, beyond being able to just optimize incremental CPA, actually has additional other important benefits. I just wanted to sort of highlight a few. So because we're running inference on every single piece of inventory, we can dynamically price each piece of inventory based on its predicted value. So this just leads to greater efficiency in your spending. Because deep learning models are capable of recognizing multiple clusters, this kind of gets at what was on the last slide. Logistic regression models are simple. Deep learning models are more complex and therefore can identify multiple clusters in your data, which allow our models to scale better to large budgets and just generally scale better. Also highlighted on the previous slide, the models are able to fully exploit your data better than simpler machine learning models or manual approaches. Because models can be retrained frequently, hourly, nightly, an algorithmic approach allows models to adapt to new inventory and changing environments much faster than manual approaches. So the perfect example of this is what's happening with coronavirus and the changing inventory that's available and the chasing user interests. And lastly, because inventory is selected based on its predicted ability to drive real KPI or actual like return, fraudulent sites, impressions, and users are more easily ignored. So that's just to highlight a few additional advantages beyond the ability to optimize incremental CPA. And so with that, let me summarize what I think are the main take-homes from my presentation today. So first of all, incremental CPA provides an accurate measurement of performance, even in complex multi-channel settings. And the key there is accurate measure of influence, not just a sort of correlation with people converting. Second, the data that one needs to collect in order to measure incremental CPA, the control group data or the PSA data, actually has multiple uses. So in addition to letting you measure incremental CPA, it actually provides critical baseline data necessary for measuring where your ads are effective and optimizing towards that. And then finally, deep learning offers unique pattern recognition capabilities that allow these data sets to be fully exploited in order to drive lower incremental CPAs, which is the technology that Cognitiv has spent so much time bringing to bear on the industry. And so with that, I'd like to thank you again for taking the time to listen, and I hope everyone stays healthy, and now I'll take questions.
Awesome. Thank you so much, Aaron. Yes, we're going to have you stick around for a little bit of Q&A, but I just want to thank you so much for joining us today. I know our audience really appreciates your time.
Thanks.